Welcome to another video explaining the universe using the particle model. Well, today's video I'm going to present results of the 18 tests that I've done where I'm looking at seeing the effective current as the G1 speed through a resistor is increased. But before we go ahead and do that, I would like to go ahead and present some information about the book that Dave and I have written. Yes, the name of the book is Principia Mathematica, and it's available on Amazon. You can get it in hardcover, paperback, or as an ebook. I recommend that if you've been interested in any of the videos that I made, that you will find this book quite interesting. Now, I'm skipping some of the other usual things I normally go through and get right to the point. I have presented in the past the fact that there are three sets of equations that can describe the function of this circuit, and in particular, the current flowing through it. And one of those are the standard equations that everybody used, that I used for 40 years, which shows that the current around the circuit is the same, whether the current through the S2 shunt resistor, R1 resistor under test, S1 shunt resistor, they're all equal. They're all based on Ohm's law very simplistically. And they work. They're quite good at working. And the result of that is that the current through the IS1, the R1, and the S2 are all exactly the same. And the example I apparently got this from, involved a 1.249 milliamp current. That's what you would see, a straight line, if you graph it. But I also have equations from TPM where I don't include the speed of the G1. The G1 flows around like the electron in the opposite direction. And these are the equations for how many G1s are flowing. A enters the battery, B leaves and enters the S1, and so on around the circuit. And these are the equations. And and what happens here is that every time you go through the battery, you add a certain number of G1s. Every time you go through the S1, you lose some, and you lose some again, and you lose some again. And what that suggests is that your current is going to be higher here than lower, because there's fewer G1s flowing through it. And as a result, you get this type of curve. Same equations. The current through the S1 is higher, then goes lower, and then lower again. So if the circuit behaves like TPM suggests, you should see curves like this when I do the measurements. Or if it's standard, you'll see a straight line. But then I added speed to the concept, and I've done this because I found out that doing the diode and the transistor, speed will help me explain the IV curve of those devices. So in this case, I've added the speed factor here. I call it SF, and it's based on the G2 mass of the R1. This M2R is the G2 mass of the R1 in units of G1. Equivalent, how many equivalent units of G1 do you have? And if you have 0 G1s here, then there is no speed reduction. But as B1 adds more and more, you get a smaller and smaller fraction, and the resistor will easily pass through, and it'll lose less. So the voltage drop through the resistor should drop. And this is what exactly happens when I do the spreadsheet and calculate this and put an assumed value here. I get this V-shaped curve. So I got three sets of equations. Standard, which is also shown here in red line here. This is standard one. You have the TPM equations without speed, where it starts high, goes low and low. And you have also this V-shape, three sets of equations. But when you measure, the circuit doesn't know anything about equations. We're going to see how well the measurements match any one of these three. I did explain this briefly about the G1 speed. As the G1 current increases, the F2 force around the resistor increases, which increases the average speed of the G1s through the resistor. An increase in speed causes G1s to pass through more easily. They lose less, the voltage drops, the current drops. And as I said before, this theory helped explain the IV curve of the diode and the transistor. Okay, so I did 18 tests. I had three resistors. The first one was 3,900 ohm. Second one was 2,200, and then 1K. I select a one, and then I apply 5 volts to it and measure the voltages. I actually measured the resistances of all the resistors, a 4-wire measurement to know what the resistances are, so that when I apply the voltage, go around the circuit, measure the voltages, I can immediately calculate the current. And I have 6 different voltages, 3 different resistors. That's 18 tests. And this is the lab. I showed this the last time. This is the signal generator I'm not using, an oscilloscope I'm not using for this test. I am using the power supply. It applies power here. This is the circuit, and this is S1, a shunt resistor, where it's there basically to measure current. This is the resistor under test, R1. And here's the second shunt resistor, and then I got a yellow strap over here to bypass the rest of that. And most importantly, a 7.5-digit multimeter, because I'm measuring, looking for differences down in the microamp and maybe even smaller range. So I used that. I did this with 3 different resistors, set it at 6 different voltages. And as I pointed out, the predicted graphs show that if the measurements look like this, then we're saying that the circuit acts as if it was following the particle model without speed. If the circuit goes like this in a straight line, then it means the standard equations that everybody knows, Ohm's law and so on, apply. But if you get a V-shaped curve, then you're matching the TPM with the speed factor applied. So what were the results? Out of the 18, 17 of them showed up with V-shaped curves. One of the 18 showed up, this is what it shows, and it certainly looks like TPM equations here without the speed. That is very straightforward. I find it odd, however, that 17 follow 1, and this one is the odd man out, so to speak. It's to the extent that we're talking about a match with TPM equations with speed, this is an error. But you literally have to interpret this as one of them, one measurement the circuit decided to behave this way, and all the rest of them that way. Now, these are two specific examples here. This is circuit 1 at 10 volts. So this is circuit 2 at 15 volts. I call that the failure in a sense because I only got 94% correlation. I'm going to show you 4 more. Here's circuit 3 at 5 volts, circuit 1 at 25 volts. And you can see they're V-shaped, but they're different. So I'm looking only at the shape of the curve to see if I can identify which one of the 3 sets of equations is apply. And again, it applies here. And this is the next one, circuit 3 at 5 volts and circuit 1 at 25 volts. So I could go through and show you all 18. It'd be boring. I just showed a few more to make the point that, yeah, 17 out of 18 were V-shaped. Now, the shapes are not exactly the same, and so I'm not talking about values here. That's going to be my next step, to talk about the values. All I'm saying is that the shape of the curve matches the TPM equations when I include a speed factor. Oh, I'm sorry, this was the second pair. Okay, now I'm going to go over a little bit of detail. One, I generated this composite graph, and I used circuit number 3 at 5 volts. And these aren't the equations. Yeah, they're equations, but they're also the values that I measured. Did a 4-wire measurement. I used the same value for S1 for all 18 tests. S2, I used this value all the way through, 4-wire measurements. Circuit 3 supposed to have a 1K resistor. Well, it actually turned out to be a 98.9 or 989 ohms, and but you have to use that. That was the whole point. And I measured the voltage applied, even though I set it at 50. The 7.5 digit voltmeter showed that it was 5.052 volts. Well, if you take this voltage and divide it by the sum of these resistors, you see you're going to be drawing 5.096 milliamps. And if you look at it over here, this line right here, that's like the standard model right there. Well, the calculated model that I calculated had a V-shaped curve, but in this scale, that V-shaped is very flat, only because it had to accommodate this larger one. So this is the calculated version using these values. But what was measured was this, way up here, all the way to down here and over there. Now, what was interesting is how far off I was, because I made some assumptions about the G2 mass of the resistors, of all 3 resistors, of these 3. I made the assumption, and I don't know if I was right. It looked like it gave me a reasonable results when I looked at the spreadsheet. But when I took the value of this, I have the values for these points in the spreadsheet. So I took this value, subtracted that value, and the difference there is only 8.5 microamps. But here's the question. Can I adjust the M2 mass of these resistors such that, and primarily probably R1, if I could adjust R1 to go from this value down to here by adjusting the G2 mass of the R1, I'm guessing that the value here will move up as I move this down. That's just a preliminary guess on my part. So that's my intent next time, and I'll let me go through what I'm going to have to do. There's a separate issue before I can actually do that, and that's because a month ago or more, I figured out that the product of my 2 constants the volts per G1 and the interaction factor had a fixed value. So if I increase VG1, I have to decrease IFR and vice versa. And I used this throughout the calculations when I made the projections. The problem was it was done without speed. So now I'm going to add speed in, and I don't know how this is going to play out, but I'm guessing that this number is going to change. So I'm going to make one shot at changing it. Then I'm going to go off and do the changing of the mass. I'm going to adjust the S1 value and do the calculation, and then adjust the M2 value and see if I can get this curve, this small V-shaped curve, the projected one, to match this one. And I got a feeling it's going to be an iterative process. I got to pick one of the 18 values, like the one I just showed you, the circuit 3 at 5 volts, and go through this process and see if I can home in on this curve. So in conclusion, I did 18 measurements. 17 matched the TPM with speed. 1 matched the TPM without speed. Maybe that was an error on my part. Maybe the circuit glitched somehow. I don't know, but it certainly looked like it matched without speed. Then I'm going to find new values for VG1, IFR, and for the G2 mass. And the G2 mass of R1 and S1 is what gives me the speed factor. And as I said, it may be an iterative process until it matches the values. My name is Bob D. Hilster, and I am your particle model guru. If you have any questions, ask Particle. Thank you for your attention.